And tomorrow is going to be kind of a hang loose day. Okay, now I have it again. I have an empty test 5 practice test. And then I have a key for it as well. So I'm going to go over the key today. Send files, test related. Okay. Now, as I was saying before, the emphasis will be on Unit 5, solutions and acids and bases. So it's crucial you go over practice problems on this. I have a ton of them in Canvas files under Unit 5. You'll see quite a few of them. And if the one you download and look at doesn't have a key to it, just choose another one. Some of them don't have keys for some reason or other, and most of them do, though. I like to have the answers for you. Okay, so first one is a titration problem. With a titration problem, you have to know what kind of titration it is. We've only covered acid-base titrations, but again, there are other ones. There's oxidation reduction titrations. There's titrations you do when you go get your allergies checked. They put these little dots of antigen on your skin, and then depending on the size of the redness, that's the titration. It's called a titer. Okay, for at endpoints with acid-base titrations, the moles of the acid equals moles of the base. So that's pH 7. That's also called the equivalence point. Okay, so we're going to start. Moles acid equals moles base. Okay, and remember the relationship between volume and concentration. When you multiply the volume, which is this, times the concentration, you end up with moles. So that's what we're going to do right here in the second step here. Now, what we don't know is the concentration of the acid. So that's the unknown. So we have, and everything is in liters. Molarity is defined as moles per liter. So make sure everything is in liters. We're going to convert 20 milliliters over to liters times the unknown concentration of acid equals the volume, the milliliters of base. Okay, so this is moles of base on the right, moles of acid on the left. What we don't know is the concentration of the acid. So we're going to solve for concentration. Which is the same as dividing both sides by O2. And that's how we ended up with this guy here. Let me redo that calculation to verify. I tend to do these very fast. So as you know, I do make mistakes. Yeah. So that's the unknown concentration of acid. Now remember, this practice test is going to be very similar to your test 5. The only thing that's not on this is going to be unit 4 questions. There'll be one of those questions on here as well. It's a simple stoichiometry. Moles on what side?
0.00567 times 0.234. Yeah.
Okay, and then did you divide by 0.02? Because 0.02 is on the left. It's 0.02 times acid concentration. You need to isolate the acid concentration by dividing both sides by O2. How did I get it? This comes from that there.
Oh,
Okay. Yeah, you divide both sides by O2 to isolate M. Now, I didn't show that step. You know, it would basically be and then those cancel that way, isolates the M. So you go 0.567 times 0.234 divided by O2. And you get this 6.63 times 10 to the minus 2. All right, what's an acid-base indicator? It determines when the reaction is at the neutral point, which is pH 7. And that's also called the endpoint. That's when we get our pink color. Equivalence point is the official moles equals moles, acid base. And the indicator indicates when that equivalence point is met. So from the indicator's perspective, it's called an endpoint. From the reaction's perspective, it's called the equivalence point. And they should be the same if you have a good indicator. And if they're off, well, then your calculation is going to have an error built into it.
or
Yeah, and phenolphthalein is a really good acid-base indicator because it's really close to pH 7. It's not perfect, but it's really close.
all the acid bases start near pH 7. That's why it turns pink when
The pH 7 is when moles of acid equals moles of base.
Yeah.
And if that's true, there's no more H or OH around.
because it gets
They don't cancel when they just turn to water. It's sort of like canceling, yeah. Okay. I'm going to do this one last. You're going to have an extra credit problem. Basically, we're going to dump some acid together and dump some sodium hydroxide together, and they're not going to be equal. So I want to know what's the final concentration of either OH or H. I'm going to do that one last, though. Let's okay, describe a solution. Two or more chemicals homogeneously mixed as opposed to heterogeneically mixed. Okay, homo means you can't tell them apart, like vodka, water and ethanol. You can't tell the water from the ethanol, perfectly mixed, as opposed to vinaigrette, oil and vinegar. That is a heterogeneous mix, definitely not a solution. Describe a solution that has more than two solutes. A solution is made up of two things, solvent and solutes. There's only one solvent, that's the one that's most Solutes are then mixed in with the solvent. You can have minimum of 1, but it can go up to 50. A good example of a solution that has multiple solutes is the air we're breathing. It's got nitrogen as a solvent because that's the predominant gas.
Don't expect us to write that. Right? Just expect us to write how the solutes and the solvent pair up. You just, like, if I could just say like water, sugar, and salt.
Yeah,
Yeah, right.
yeah, that would be a good example of more than one solvent. Okay, his example was water being the solvent, and the two solutes are salt and sugar, right?
Yeah.
Yeah, you mix those all together, you can't tell where the salt is or the sugar. Or you could put 2 different salts in. You could put potassium chloride in there, sodium chloride in there. There's a lot of examples of multiple solutes. Most of the time, our world is mixed solutes, not one solute. Acids dissociate H+, bases dissociate OH-. So that's the difference between an acid and a base. Depends on what comes off. Depends on what disassociates from the original compound. If it's an H, it's an acid. If it's an OH, it's a base. All right, how would you make 9+ liters of 0.23 molar solution of acetic acid from dry ingredients? I want directions there. How would you make? So that means you're going to have a answer that looks like that, not just some calculations. Okay, so concentration is 2 parts, moles and volume in liters. Moles and liters. Okay, so the first thing we need to do is figure out how many moles of this C2H4O2 is. Okay, so you need to find, since we're starting from solution and we have volume, remember volume times concentration gives us moles. There's some real important relationships for Unit 5. One is that's number 1. You're going to use that all the time. When you're doing titration calculations, same thing. You're talking about neutralization. One mole of acid neutralizes 1 mole of base. There's an assumption on that. That's for monoprotic acid. That means only 1 H comes off, not 2 or 3. 1, that's why HCl is frequently used as a monoprotic acid, mono being 1. Sulfuric acid, 2 come off. Phosphoric acid, 3 comes off. Citric acid, 3 comes off. So you need to know what your acid is, because they're not all the same. But for our class, we always use HCl. So 1 mole of acid neutralizes 1 mole of base. If it was sulfuric acid, which is a diprotic acid, 2 come off, then 1 mole of acid is neutralized by 2 moles of base. Okay, so it depends on how many hydrogens are coming off. Let's see, what else?
Which one's an example of that, please?
Of what?
Acids and bases.
Okay, so hydrochloric acid is a monoprotic acid. Only one H comes off. Sulfuric acid, that's a diprotic. So that means 2 H's come off. So phosphoric acid, 3 H's come off. Triprotic. No, because we're only going to work with monoprotic acids. I'm just saying though, that assumption up here is for a monoprotic acid. But there are diprotic and triprotic acids out there. So in 1A or 3A, you're going to run into di and triprotic acids. And you have to just remember that for every H that comes off, you have to match it up with an OH. So if 2 come off, you have to have 2 OHs to match them up. Because then they form water each time.
Right. So the acid is the H minus or the H plus.
Yeah.
And then the base is the
OH.
minus.
Exactly. Okay. Okay, so one way to make solutions with dry ingredients, the other way is by diluting a concentrated solution. Okay, so this is what we're doing here. How would you make, again, I want directions. I didn't have room, I was writing it. But I'll write the directions on the side here. How would you make, same thing, 905 liter solution of 0.23 molar solution of acetic acid from 11 molar concentrated solution. So now we're starting with a really concentrated solution, diluting it. So moles of concentrate equals, in fact, we should put that over here. So moles of concentrate equal moles of dilute. That's what you're going to start with. Okay, so the moles of concentrate is, we don't know the volume of concentrated stuff to start with. But we do know the concentration of it. We don't know how much volume, okay? So the concentrated is 11.3 moles per liter. And multiply that by the unknown liters gives us moles. And that's equal to the dilute side, which we want 9.05 liters at 0.23 moles per liter. So now we're going to solve for L by dividing both sides by 11.3 moles per liter. Notice what happens when we divide. We multiply by its inverse. So when that comes over to the other side, it's inverted. Okay. All right. So that isolates the concentrated liters and ends up being 0.184 liters of concentrated. Now, then we have to add water to bring it up to 905. So we subtract the concentrated volume from the dilute volume that we want to create. That leaves us 8.87 liters of water.
Because
So we're going to take 0.184 liters of the concentrated stuff. In other words, 184 milliliters, dump it in the jug, and then we're going to add 8.87 liters of water to bring it up to 905. Because the 905 includes two things. It includes water plus the concentrated solution. Yeah, so these two are in there. Well, because I told you in this solution. So in here, we always do solutions of water. When you take organic chemistry, you can be doing solutions of other solvents like pentane or chloroform or
I'm sorry. Solvents, right. That is solvent.
yeah, the solvent in fact in 1A and 1B and A and 3A, all of them are the solvent's always going to be water, but it can be other things as well.
I just assumed it's water.
Yep, exactly.
It's not asking for the solvent. It's not saying solvent.
Well, the water is the solvent.
Right.
So it is asking for the solvent.
What word?
Hmm?
How do you make this? That
Okay, I'm going to do directions right now. Okay, we're going to mix 0.84 liters of concentrated solution in, not two, in 3 liters of water, but it doesn't have to be 3. It can be 4, 5, 1, as long as it's not 9. It has to be below that. So the 3 liters can be any amount, okay? Make sure it's thoroughly mixed, and we bring the final volume up to 9.05 liters. That would be the answer. I want directions. Okay, describe in detail how a cube of sodium chloride dissolved in a water solvent, including both verbal description plus the diagram. Okay, here is the verbal. But before I talk about that, So sodium chloride is an ionic solid. That means it's composed of sodium ions and chloride ions. And water, as I've told you before, is very polar. As you remember, whenever we have oxygen present, the molecule tends to be very polar. Not 100% of the time, but usually it's very polar. That means that there's an unequal sharing of electrons. That means the oxygen is a little more negative than the hydrogens. That's what makes it polar. So what's going to happen is the polar water molecule is going to pull out the ions in the sodium or in the salt. So the oxygen is going to be attracted to the sodium, and the hydrogen will be attracted to the chloride. And because the water is vibrating, it's going to pull it out. So the more it vibrates, higher temperature, the more it vibrates, the odds of it hitting the salt crystal is greater. That's why heating the solvent increases the motion. That increases the odds that that water is going to hit. Over here. Partial, as opposed to a full +1. It's like a 0.25 plus. Yeah. And it varies depending on what combination you have. There's something called electronegativities for the O and electronegativity for the H. You take the difference between the two, and that determines what the partial charge is. But 1A stuff, okay? The main thing to know is that if you have an ionic crystal like sodium chloride or sugar, also very polar, a polar solvent will dissolve it. Remember, like dissolves like. So water is polar, salt is polar. And I summed it up in a paragraph over here. So as the water bumps against the ions, it will pull the ionic solid apart. The more water bumps into the ionic solid, the more not move, but more. The more the solid will dissolve. Temperature, physical agitation will increase the number of impacts, so it'll dissolve faster. Increasing the surface area will also increase speed of dissolving. Okay. Powdered sugar versus granulated sugar. Okay, so let's go on here. Okay, so what's the hydrogen ion concentration of the following acidic solution? Okay, we throw in 3.45 grams of hydrochloric acid and throw it into 2.34 liters of solvent or water. Okay, so first thing we need to know is moles of HCl. We need, since it's dry, not wet, it's dry, we need the molar mass of HCl, which is 36.46 on the left over here. Molar mass. No. We know the we need to know the volume though. Okay, so it gives us moles all over 2.34. So here are the moles. As I said, grams.
Oh,
If I said it was wet and said it was grams, you need to know the density to calculate volume. Mass over volume for density. Okay, so we've got, so in a reaction like hydrochloric acid, if we know the moles of that, we know the moles of that and the moles of that. Because the relationship in the balanced equation is 1, 1, 1. So 1 mole of HCl equals 1 mole of H, also 1 mole of Cl minus. So moles of HCl equal moles of acid. Now here we want hydrogen ion concentration, H plus. Okay, so that's 9.46 times 10 to the minus 2, or 0.9496, all over 2.34 liters. Grind that out and it ends up being 0.0404 moles per liter, or molarity. Okay, notice we went from 10 points to 15 points. Whenever you see that increase in points, assume the problem is harder or has more steps. Okay, so we've got two things going on here. We've got one concentration of sodium chloride at 2.34 liters, or 256 molar, plus we dump in another 4.56 liters of 1.29 molar. Mix them together. What's the final concentration? Well, we need moles contributed from each one. So solution one, if solution one and we have solution two. So solution one, the moles is volume times concentration, gives us moles. Solution two, we want moles, again, volume times concentration, totaling 1187 moles total. And what's the final volume? Final volume is going to be 234 plus 456 is 6.90. So now we have moles per liter. The two, add those together. Yeah, that's where you get that. Okay, so we've got 1187 moles over 6.9 liters. 1.72 moles per liter, or 172 moles per liter molarity. Now, this problem is going to be the hardest problem that you're going to be responsible for. However, for extra credit, there's this one. Correct. That's why it's extra credit. But it's basically very similar to the last one. You've got moles from the acid, moles from the base. The moles are not the same. So one of them is greater than the other. In this case, there's more acid moles than there are base moles. So that means we have 0.240 moles of acid left over, non-neutralized. And we have a volume of 485 after we add those two together. So we have moles per volume. So calculations are the same as that last one, It's just, you have to understand the concept of the neutralization going on with the H and OH. Now, in a normal semester, you'd be responsible for that. But because we are summer, we're zooming through this. I'm just gonna not hold you responsible for that. Except unless you want to do extra prep. Yeah. Any new ones? No. I'll bring new ones tomorrow. Yeah, they're there now. Yeah, if you go to files, unit 5, you'll see a whole bunch of them on. I mean, you'll probably see 20, 25 of them, including titrations, mixing stuff up. And that's where those worksheets from yesterday came from. Additionally, as I was saying earlier, not necessarily all of them have the answers though. So just go to the next one if it doesn't have answers, or send me an email and I'll make a key for it. All right, that's what I wanted to cover today. Now Thursday's test, theoretically it's an hour test. But I'll give you 2 hours to do it, okay? Up to 2 hours. That should give you plenty of time. Now I did this test this morning. And what I do is I take the test and then I multiply the time it takes me to do the test by 4. And that's how long I give everyone. So it's basically an hour test. And I'm giving you 2 hours.
Could you please scroll up?
Which way? Up?
Thank you.
And both, the key is posted in files as well as the unfilled out test. So you have both of them there. One's a key, one's not.
This extra credit, what does it mean by whatever it's?
Well, I'm just saying, I'm dumping in acid, I'm dumping in base.
Yeah.
One's going to be more. This is how to find out which one is more. Calculate moles, because it's 1 mole of acid, 1 mole of base makes water. So that's where those are neutralized. So you need to find out how many of each you have, and then you'll have an excess. And that's what you use to calculate the concentration of the H in there, because it's more acid than base.
Solving. Oh, and then you add the excess with whatever's.
The volume from each one contributes, yeah.
So you add the excess to whatever's already equaling each other.
Those cancel out.
Okay.
And you say, okay, what's left over? One's going to be more than the other. In this case, when you calculate moles, you have 10 moles and basically 8 moles. You have sort of 2 moles left over of acid. And then use that to calculate concentration. And then the volume, you always need volume.
So if you do 10 and 8 moles, how do you
Okay, so you've got, when you subtract the 2, you've got 2.4 moles of excess acid. Because we have more acid than base by 2.4 moles. Everything else is neutralized. So now we're down to the bottom here. We need to know the final volume. Final volume is 285 when we add these two together. So now we have moles volume. Want to know the hydrogen ion?
Oh, it's more high.
Yeah, then it says whatever is more. Did you see that?
So you need all that.
Yeah, exactly. Well, we ended up with more moles of acid than moles of base. By how much? 2.4. So that means there's unreacted H pluses running around. That kind of flow, you just need to do it. Right? Yeah. Your tests. I've given back all the test scores except for the.
Yeah.
Oh, I see what you mean. You can get it back. I mean, I'm here in the fall, or I can scan it for you and email it to you. How does it do that? Huh?
Got to your shirt.
That's pretty cool. All right, so that's it for today. So if you haven't checked out of your drawer, I'll meet you over in the lab. The room is open. So get all your stuff out. And there are some yellow sheets. There's some yellow sheets in there that you have to leave in the drawer of the inventory. Okay. Then I need to grab your stuff for which lab was it again? The double replacement, right? Yeah.